Have you ever stopped to think about what's actually happening inside your computer? I mean, really think about it. It's a machine, right? A collection of circuits and wires. And yet, we type words and it creates entire worlds, calculates complex problems, connects us across the planet. So, how does that happen? Let's pull back the curtain on one of the biggest mysteries of our digital age. It all starts with something that looks a lot like this. This is a super simple program written in a language called C. Now, even if you've never written a line of code in your life, you can probably guess what this does, right? It's telling the computer to show the words "Hello World" on the screen. It's readable, it makes sense to us, and it's our first clue in this investigation. But that brings us to the real head-scratcher. A computer doesn't understand English. It doesn't understand C or Python or any language we speak. At its very core, it's just a box full of millions, even billions of tiny little switches that can either be on or off. That's it. So, how in the world do we get from a word like printf to a bunch of electrical signals? Well, the first piece of this puzzle is the whole idea of a programming language itself. You got to think of it like a specially designed bridge. It's a formal, really structured language that lets us humans write down our ideas and our logic in a way that can be systematically translated for the machine. It's the middle ground. But not all of these bridges are built the same. They exist on a kind of spectrum. On one end, you have high-level languages, like the C we just saw or Python. They're closer to English. They're designed for us, for programmers, to read and write easily. Then, on the other end, you have low-level languages. These are much, much closer to the machine itself. They look cryptic to us, but they give you direct, raw control over the hardware. So, we have our high-level C code, but the computer needs those low-level instructions. How do we get from A to B? We use a special program, a translator. For a language like C, we use something called a compiler. And the best way to think about a compiler is to imagine it's translating an entire book. It takes the whole program, every single instruction, all at once, and translates it into a brand new file of pure machine code before anything can even start to run. And the results of that translation? Well, it's a seemingly endless stream of zeros and ones. This, right here, is binary, the native tongue of the computer. That human-readable Hello World program, after the compiler does its job, turns into a long pattern of zeros and ones that the machine can finally understand. Okay, so this is the absolute key, the magic link between the abstract and the physical. Binary isn't just random, it's a number system, base 2. And those two digits, 0 and 1, they directly map to the only two states a circuit can be in. A 0 means the switch is off, no electricity. A 1 means the switch is on, electricity is flowing. This is literally the point where software meets hardware. And this shows perfectly how it works. It might look a little intimidating, but it's really not. You know, in our everyday decimal system, base 10, each spot has a value. The ones place, the tens place, the hundreds, and so on. Well, binary is the exact same idea, but with powers of 2. You have the ones place, then the twos place, then the fours, then the eights. So the number 13 in binary is 1101, because you have 1 8 plus 1 4 plus 0 2s plus 1 1. See? It's just a different way of counting. And these ones and zeros are the fundamental atoms of all digital data. A single 0 or 1 is called a bit. You group 8 of them together and you've got a byte. And anytime you hear words like kilobyte or megabyte when you're talking about file sizes, you're really just talking about thousands or millions of these simple little bytes. Okay, so we know how to turn numbers into binary, but what about the actual letters in Hello World? That's where something called character encoding comes in. Just think of standards like ASCII or Unicode as these giant dictionaries. They basically assign a unique number to every single character you can think of. The capital letter H is assigned the number 72. The lowercase e is 101, and so on. And once we have those numbers, well, the computer knows exactly how to convert them into binary. All right, let's put it all together. Here's the entire journey, from our brain to the machine's brain. First, we write our human-readable source code. Then, the compiler translates all of that into low-level machine code, which is just binary. The computer's loader then takes those binary instructions and puts them into memory, or RAM. And finally, the CPU, the central processing unit, reads that binary from memory and executes the instructions, flipping its little switches on and off at incredible speeds, from a word to a flicker of electricity, just like that. You know, when you step back and look at it, it's pretty mind-blowing. In the end, it's all just zeros and ones. every photo on your phone, every song you stream, every complex video game, it's all just an incredibly clever, unbelievably vast arrangement of on and off switches. It's the simplest possible foundation, but it allows for infinite complexity. And that leaves us with a pretty big question. Knowing this, what will we teach these simple zeros and ones to say next?